Hello everyone. I hope you all are doing well. And today we are back again with part 2 of the series that we have started for the assembly language programming. So today we will be having a look at instruction addressing and execution. So today we will try to understand the general requirements for loading and executing programs on the computer. So the first topic that we have is the system program loader. So in Windows operating system, so for this video we will be referencing at the DOS programming, the DOS operating system, the Windows DOS, and in that operating system, the two types of executable programs are the COM and EXE. So both are the executable programs, and a COM program consists of one segment that contains code, data, and stack. A COM program, it will contain like all of these segments uh, in a single segment. In real mode, an EXE program consists of separate code, data, and stack segments. So when you're executing these programs, when you request the system to load a exe program from disk into the memory for execution, the loader performs the following steps. So the first step it will do is access the exe program from disk. So again, this is specifically we are talking about the DOS operating system. So in the first step, it will access the exe program from the disk. In the second step, it will construct a 256 byte program segment prefix on a paragraph boundary in the internal memory. So again, this program segment prefix is something that the programs, all the uh, data structures and the information required by the CPU for accessing the different parts of the program, it's stored in this area. So this is the data structure that is initialized in the second step on a paragraph boundary. So paragraph is like 16 bit multiples of memory. So for easier and faster access, it is loaded on the paragraph boundary of the internal memory of the system. So in the third step, it stores the program in memory immediately following the PSP. In the fourth step, it will load the address of the PSP in the data segment and the ES register. Then in the fifth step, the operating system loads the address of the code segment in the CS register and sets the IP register, instruction pointer register, to the offset of the first instruction. So usually it is 0 in the code segment. Then in the sixth step, it loads the address of the stack in the SS register, stack segment register, and sets the SP register, the stack pointer register, to the size of the stack. Then in the last step, it will transfer the control of the program. It will transfer the control of the execution to the program, and it will usually begin with the first instruction in the code segment. So this is how a program segment prefix looks like, the one we had discussed in the previous slide. So as you can see, it contains a lot of information about the program itself and the information that may be required by the operating system to execute the programs. execute the specific program that is in the execution phase right now. So all that information, it can be found in the program segment prefix. So this is again specific to the DOS operating system. So the newer operating system that we have today have different data structures which store this type of information. So let's talk about stack now. Both COM and exe programs require an area in the program reserved as stack. So the stack mainly has three uses. The first being the program calls a subroutine for special processing, and in doing so, it saves the return address in the stack. Whenever the subroutine it wants to run, it will store the return address in the stack, and once the subroutine has been completed, it should know where the program should return to continue the execution. So this it will refer in the stack, and then from there it can return and continue the remaining flow of the execution. The second use is the program that calls the subroutine may also pass some data by placing it in the stack. So the subroutine that is being called, it is possible that the calling program might have to pass some data to the subroutine, and it can be stored on the stack. And when the subroutine is being executed, it can access that same data from the stack itself. And the third use that we have is the program has to perform calculations that use registers. So what it can do is it can save the present contents of the register on the stack, make the calculations in the subroutine or in the same program itself, and then restore the data from the stack back to the registers after the calculations are complete. In real mode, each data item in the stack is one word. So one word, that means 2 bytes. The stack differs from other segments in its method of storing data by it starts storing the data at the highest location in the segment and stores data in the subsequent cycles by going downward through the memory. So we will have a look at this using an example now. So there are two types of instructions, so push and pop, that modify the contents of the SP register and are used for storing data on the stack and retrieving it. So push executes by decrementing the stack pointer by 2 to the next lower storage in the stack, and if we are pushing any values, then it is again like decremented by 2, and pop, when we are popping any values, the value of the SP is incremented by 2 to the next higher storage word. So according to the example we have here on screen, we have the stack pointer pointing at 36. So initially the stack is empty and looks something like this. Here we have the offset values. So the segment address of the stack in the SS does not concern us here. This is just for like a basic understanding. So these are the offset values for the different positions in the stack, and the stack pointer is currently pointing at 36. And the AX register currently holds this value 0 to 6B. So let's say we perform an operation which is push AX. Okay, so what this will do is it will decrement the stack pointer by 2. So it will be like from 36 to 34, and store the contents of AX, that is 0 to 6B in the stack. So again, 026B, it's the contents of the register, and whenever it is being stored, the stack is in memory. Whenever it is being stored, it will be reversed, the bytes will be reversed. So in the stack it will be stored as 6B02. Then if you see here, we have another register BX which is holding the value 04E3. Okay, so when we execute the next instruction, that is the push BX instruction, again the stack pointer will be decremented by 2 and it will go to the value 32 now, and it will store the contents of BX, that is 04E3, as you can see here in the stack frame as E304. So next instruction, if we run as pop BX, so it will restore the word from where stack pointer points in the stack, that is the E304, to BX, and it increments the stack pointer by 2. So the value goes back again to 34. And similarly, if we next run the next instruction as pop AX, the 6B02 means it will be again sent to the AX register, and it will be storing as 026B. So again, one thing to note is that the pop instructions are coded in reverse sequence from the push instructions. So in the example, we pushed the instructions AX and BX, but while popping them, we popped them as BX and AX respectively. Also, the values pushed onto the stack are still there. Although stack pointer no longer points to them, but the values are still there in the stack itself. So subsequent push operations will replace the old values with the new ones. Also, one thing to note is that when stack pointer becomes 0, the stack becomes full. Other stack related instructions are like push F and pop F. So these save and restore the status of the flags. Then we have push A and pop A. So this push A and pop A is an instruction that is available on the processors after 80286. So this instruction saves and restore the contents of all general purpose registers like AX, CX, DX, BX, SP, BP, SI, DI, and it will increment or decrement stack pointer by 16. Then we have push AD and pop AD. So this instruction is available on the processors following 80386. And this instruction saves and restores the content of all extended registers. So extended registers being the 32-bit registers EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. And it will increment or decrement the ESP by 32. Instruction execution and addressing. So the basic steps that the processor takes in executing an instruction are: first, it fetches the next instruction to be executed from memory and places it in the instruction queue. So this is the instruction queue that we have here. And then in the second step, it will decode the instruction, calculate the address that reference the memory, and deliver the data to the arithmetic and logic unit and increment the instruction pointer register. And in the third step, it will execute the instruction, perform the requested operation, store the results in the register or memory. And if there are any flags to be set, it will do the same in the same operation. So in the, like we discussed yesterday, in the Pentium's pipeline capability that it was introduced in the Pentium processors, it enables the processor to overlap operations. So as you can see in the figure here, when a processor is performing a single instructions, it can do multiple instructions parallelly. So let's say in the first cycle it is doing fetch for the first instruction, and in the second cycle, in the second step, it is doing decode of the first fetched instruction. But along with the decoding of the previously fetched instruction, it will also fetch the next instruction that it has to decode. And when it is executing the first instruction, it will decode the second instruction that is fetched, and then fetch one more third instruction that it will decode in the subsequent cycle. So as already discussed, for an exe program, the CS register, the CX register provides the address of the beginning of program's code segment, and DS provides the address of the beginning of the data segment. The code segment contains instructions that are to be executed, whereas the data segment contains the data that the instructions will refer. Then we have the instruction operands. An instruction may have 0, 1, 2, or 3 operands. So let's have a look at this using an example that we have here. So in the first line that we see, the first move transfers the data between the memory and a register. So in this we are defining word X as a word, if you see here, and we are saving 0 in it. In the second move, it transfers the data 25 into the register CX. Then in the third instruction, the third move transfer, it will transfer the data between the registers BX and CX. So the value of BX, it will be transferred into the CX register. And for the fourth instruction, the square brackets in the fourth move instruction define an index operator, which means use the offset address in BX, like the combined one with the segment address in the DS as a DS BX. So uh, the address stored, whatever is stored in the DS BX register, to locate a word in the memory and move its contents to CX. So how it differs from the previous instruction BX and the square bracket BX. So the previous instruction simply moves the contents of BX register to the CX register. But this instruction moves the contents of the location addressed by the BX register. So if let's say BX register has some address 0A3B, in the memory, whatever the contents that are there on that address present, that contents will be transferred to the CX register, the value whichever is stored. And here today we have some more information on the protected mode that we had discussed yesterday. So already we had some basic understanding about the protected mode and the features it provides, like memory protection and multitasking, and the processor is able to provide these by using some additional data structures that are being supported on the newer processors, and the first being the local descriptor tables. So depending upon the system, there is one table for each task. The 16-bit LDT register contains the address of this table for the current task that is executing. Then we have the interrupt descriptor table. So this table handles the interrupt operations. So the IDT register contains its address. And the last one we have is the GDT, the global descriptor table. And this table contains the address of each local descriptor table. And it is the 32-bit GDT register that contains the address of this table. The actual addresses of segments are stored in the descriptor tables. The segment registers or selectors contain pointer to the current local descriptor table. The tables provide 32 bits for addressing the memory, like up to 4.3 gigabytes of memory. So using these tables, it is possible for the CPU to do multitasking as well as see what memory areas can be accessed and what permissions the current running task or the process or the program has to access in the memory. So this is it for today. Thank you all for watching and see you all in the next video.